Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about basics of thermodynamics, temperature, energy, and entropy. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. What is thermodynamics? Thermodynamics is the branch of physics that explores how energy moves and changes form within a system and how systems perform work. Its development in the 19th century was closely tied to the invention and improvement of steam engines, as engineers needed a framework to predict how energy input would translate into motion and work. Unlike microscopic theories that focus on individual molecules, thermodynamics looks at the macroscopic, observable behavior of systems, properties such as pressure, temperature, and volume that can be measured and controlled in experiments. The microscopic behavior of gases, including collisions and molecular speeds, is described by the kinetic theory of gases, which complements thermodynamics by providing a deeper understanding of why these macroscopic properties behave the way they do. The laws of thermodynamics form the backbone of the field, each giving rise to specific properties and principles that allow us to analyze and predict system behavior. These laws apply broadly to physical systems, but they are particularly important in aerospace engineering, where understanding high-speed flows, propulsion systems, and gas dynamics is essential. Interestingly, the numbering of these laws can be counterintuitive, as the sequence starts with the zeroth law. The zeroth law of thermodynamics is deceptively simple but fundamental. It introduces the concept of thermodynamic equilibrium. When two systems are each in equilibrium with a third system, they are in equilibrium with each other. This principle allows us to define temperature in a meaningful, measurable way at the macroscopic level, rather than relying on the random motion of molecules. In practical terms, it explains why a thermometer can consistently measure the temperature of a system and why heat flows from hotter to cooler objects until equilibrium is reached. The first law of thermodynamics extends the principle of energy conservation to thermodynamic systems. It states that the total energy in a system can change only through heat transfer or work done by or on the system. This law introduces key concepts such as internal energy, which accounts for the energy contained within the system, and enthalpy, which is useful when considering processes that occur at constant pressure. For instance, in a jet engine, the first law helps engineers calculate how much fuel energy is converted into thrust versus how much is lost as heat. While the first law allows a wide range of theoretically possible system states, not all of them actually occur in nature, which brings us to the second law. The second law of thermodynamics introduces the concept of entropy, a measure of disorder or the unavailability of energy to do work. This law explains why certain processes are irreversible. For example, hot exhaust gases from a rocket cannot spontaneously flow back into the engine to recombine with fuel. Energy naturally disperses in one direction. The second law states that the total entropy of a system plus its environment can never decrease. In ideal, reversible processes, entropy remains constant, but in real-world, irreversible processes, it always increases. This principle is crucial in propulsion systems, as it sets the limits on engine efficiency and explains why no engine can convert all fuel energy into useful work without some loss to heat. In summary, thermodynamics provides a framework to understand energy, work, and heat at a level that we can observe and measure. The zeroth law gives us the concept of temperature and equilibrium. The first law defines how energy is conserved and transformed, and the second law introduces limits on how energy can be used efficiently. By connecting these laws to practical systems like engines, turbines, and high-speed flows, we can predict performance, optimize designs, and understand the fundamental limits imposed by nature. Okay, we have learned what thermodynamics is and what it studies. Now let's study the laws of thermodynamics in depth. Thermodynamics is a branch of physics that studies the energy and work of a system. Unlike microscopic theories, it focuses on the large-scale responses of systems that can be observed and measured experimentally. The small-scale interactions of gas molecules, such as collisions and motion, are described by the kinetic theory of gases, which complements thermodynamics by explaining the underlying molecular behavior. The zeroth law. The zeroth law of thermodynamics provides a fundamental definition of thermodynamic equilibrium. It begins with a simple observation. Certain properties of objects, such as the pressure in a gas, the length of a metal rod, or the electrical conductivity of a wire, change when the object is heated or cooled. If two objects are brought into physical contact, these properties initially change in both objects. Eventually, the changes stop, and the objects are said to be in thermal or thermodynamic equilibrium. This concept allows us to define temperature on a macroscopic scale. Objects in thermal equilibrium have the same temperature. The zeroth law also states that if two objects are each in equilibrium with a third object, they are in equilibrium with each other. For example, consider three objects. Object 1 and Object 2 are in thermal equilibrium, and Object 2 is in equilibrium with Object 3. Even though Object 1 and Object 3 are not initially in contact, they are found to be in equilibrium when brought together. This principle allows the creation of thermometers. By calibrating a device to measure a change in a thermal property, such as the length of a column of mercury, we can determine the temperature of any system by placing the thermometer in thermal equilibrium with it. Metric thermometers, like those using Celsius, set reference points at the freezing and boiling points of pure water, allowing temperature measurements of other systems based on observed changes in the thermal property. A real-world example of the zeroth law in action is checking the temperature of a cup of tea with a thermometer. When the thermometer is placed in the tea, heat flows between the tea and the thermometer until thermal equilibrium is reached. Once the temperature of the thermometer stabilizes, it matches the temperature of the tea, demonstrating that both are in thermal equilibrium. Another everyday example is using a thermostat in a room. The thermostat measures the temperature of the air and signals the heater or air conditioner to adjust energy input until the desired temperature is reached, bringing the room into equilibrium. Even the simple act of touching a cold metal doorknob illustrates this law. Heat flows from your warmer hand to the cooler metal until both reach a common temperature. In aerodynamics, the thermodynamic behavior of gases is particularly important, not only for analyzing propulsion systems, but also for understanding high-speed flows and their effects on vehicles and aircraft. When we study the work done on or by a gas, we observe that the amount of work depends not only on the initial and final states of the gas, but also on the specific process or path that connects these states. Similarly, the amount of heat transferred into or from a gas depends on both the states and the path taken. However, experiments with real gases have shown an important pattern. The difference between the heat added to the gas and the work done by the gas depends only on the initial and final states of the gas, and not on the process itself. This observation suggests the existence of a property called internal energy, which is a state variable, like temperature or pressure, that depends only on the current state of the system and not on how that state was reached. The first law of thermodynamics. The first law of thermodynamics formally defines internal energy, E, as the difference between heat transfer, Q, into the system and the work, W, done by the system. In linear form, this can be written as change in internal energy equals heat added to the system minus work done by the system. In this definition, the direction of energy flow is important. Heat added to the system is positive. Heat removed from the system is negative. Work done by the system is positive, and work done on the system is negative. Internal energy is a form of energy, just like the potential energy of an object at a certain height or the kinetic energy of a moving object. Just as potential energy can be converted into kinetic energy while conserving total energy, internal energy can be transformed into either kinetic or potential energy. Unlike heat or work, which are path-dependent and cannot be stored, internal energy can be stored within the system and represents the energy contained due to molecular motion and interactions. Although the first law of thermodynamics allows many possible states for a system, not all are observed in nature. The second law of thermodynamics explains why only certain states occur naturally. The first law of thermodynamics defines the relationship between the various forms of energy present in a system, such as kinetic and potential energy, the work the system can perform, and the transfer of heat. The law essentially states that energy is conserved in all thermodynamic processes. However, it is possible to imagine processes that conserve energy but never occur in nature. For instance, if a hot object is placed in contact with a cold object, heat naturally flows from the hot object to the cold object until thermal equilibrium is reached. One could imagine, in theory, a system in which heat flows spontaneously from the cold object to the hot object. Although energy would still be conserved in this imagined scenario, such a process does not occur naturally. Observations like this led thermodynamicists to propose a second law of thermodynamics. Scientists such as Clausius, Kelvin, and Carnot formulated different versions of the second law to address specific physical problems. In the description provided here, the second law introduces a new state variable called entropy. Entropy has several physical interpretations, including a measure of the disorder or randomness of a system, but for our purposes, we will consider it simply as another property of the system, like enthalpy or temperature. The second law of thermodynamics. The second law of thermodynamics introduces a property called entropy, denoted as S. For a reversible process, the total entropy of the system and its surroundings does not change, so the final entropy SF equals the initial entropy SI. An example of a reversible process is an ideal gas flowing through a constricted pipe without friction or energy losses. As the gas passes through the constriction, its pressure, temperature, and velocity change, but downstream they return to their original values. Since the gas returns to its initial state, the change in entropy is zero. For irreversible processes, the total entropy of the system and its environment always increases, meaning SF is greater than SI. A simple example of an irreversible process is placing a hot object in contact with a cold object. Heat flows from the hot object to the cold object until both reach the same temperature, and they do not spontaneously return to their original temperatures. If the amount of heat transferred from the hot object to the cold object is Q, The average temperature of the hot object is Th, and the average temperature of the cold object is Tc. The change in entropy of the hot object is negative Q divided by Th, and the change in entropy of the cold object is Q divided by Tc. Therefore, the total change in entropy is equal to the initial entropy minus Q divided by Th plus Q divided by Tc. Since Th is greater than Tc, Q divided by Tc is larger in magnitude than negative Q divided by Th, so the final entropy is greater than the initial entropy, as the second law predicts. If heat were transferred from the cold object to the hot object instead, the total change in entropy would be equal to the initial entropy plus Q divided by Th minus Q divided by Tc. In this case, the final entropy would be less than the initial entropy, which violates the second law of thermodynamics. The change in entropy of the hot object is negative because heat leaves the object, and in words, this is expressed as negative heat divided by the average temperature of the hot object. For the cold object, the entropy change is positive because heat enters the object, expressed as heat divided by the average temperature of the cold object. Therefore, the total change in entropy of the system is equal to the initial entropy plus the negative heat divided by the average temperature of the hot object plus the heat divided by the average temperature of the cold object. Since the average temperature of the hot object is always greater than that of the cold object, the magnitude of the positive term for the cold object is greater than the magnitude of the negative term for the hot object. As a result, the total entropy of the system increases, as the second law predicts. If instead one assumes that heat were transferred from the cold object to the hot object, the total entropy change would be calculated as the initial entropy plus heat divided by the average temperature of the hot object minus heat divided by the average temperature of the cold object. In this scenario, the total entropy would decrease, which violates the second law of thermodynamics. A common real-life example of the second law of thermodynamics is a cup of hot coffee left on a kitchen counter. Initially, the coffee is much hotter than the surrounding air. Heat naturally flows from the coffee to the cooler air until both reach the same temperature. During this process, the entropy of the coffee decreases because it loses heat, but the entropy of the air increases because it gains heat. The increase in the entropy of the air is greater than the decrease in the entropy of the coffee, so the total entropy of the system, coffee plus air, increases. This process is irreversible. If you leave the coffee on the counter long enough, it will never spontaneously become hotter than the surrounding air. This illustrates why heat naturally flows from hot to cold, and how the total entropy of a system plus its environment always increases in real processes. Heat transfer. As mentioned on the gas properties lesson, thermodynamics focuses only on the large-scale response of a system, whose changes we can observe and measure directly in experiments. In aerodynamics, we are especially concerned with how thermodynamics applies to propulsion systems, since understanding how gases store and transfer energy is essential for analyzing engines and high-speed flows. The zeroth law of thermodynamics introduces the concept of thermodynamic equilibrium. Two objects are said to be in thermal equilibrium if they have the same temperature. If we place two objects with different initial temperatures in physical contact, heat will flow from the hotter object to the cooler one until both reach the same temperature. This process of reaching thermal equilibrium always involves a transfer of heat. The amount of heat transferred depends on two factors: the temperature difference between the objects and the heat capacity of the material. Heat capacity is a property that tells us how much heat energy is needed to raise the temperature of a substance by 1 degree. Different materials have different heat capacities, which explains why some substances heat up quickly, while others require more energy to achieve the same temperature change. Importantly, heat always flows naturally from the higher temperature object to the lower temperature object until equilibrium is reached. In the case of a gas, heat transfer is closely tied to a change in temperature. The state of a gas is described by three main variables: temperature, pressure, and volume. Adding heat to a gas changes its state, but this can happen in many different ways depending on the conditions. For instance, a gas may expand, be compressed, or change pressure when heated, depending on how the process is carried out. Similarly, the work that a gas can perform depends not only on its initial and final states, but also on the specific process by which it transitions between those states. The same is true for heat transfer. The amount of heat exchanged during a process depends on both the starting and ending states of the gas and the exact path taken between them. Because both heat flow and work play crucial roles in changing the state of a system, they are combined in a single principle known as the first law of thermodynamics. This law establishes the fundamental relationship between energy transfer in the form of heat and energy transfer in the form of work. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What does thermodynamics primarily study? The correct answer is the large-scale behavior of systems such as energy, work, and heat. Question 2. What concept does the zeroth law of thermodynamics introduce? The correct answer is thermodynamic equilibrium and temperature. Question 3. According to the first law of thermodynamics, how is the change in internal energy of a system calculated? The correct answer is heat transferred to the system minus work done by the system. Question 4. What does the second law of thermodynamics state about entropy in real processes? The correct answer is it always increases in real processes. Question 5. Which of the following is a real-life example of the second law of thermodynamics? The correct answer is a cup of hot coffee cooling to room temperature. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics, and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about work, heat transfer, enthalpy, and entropy of gases. See you in the next video. Bye.